Okay, so get this. Picture a creature living in, like, boiling acid.
Huh.
Or even, thriving in temperatures that would turn your freezer into a sauna.
Yeah.
We're going deep into the world of extremophiles today.
Right.
You sent over some really wild research on these incredible survivors.
Yeah.
So let's unpack it. What do they tell us about, like, the very limits of life?
Well, and I think the important thing to remember is that extreme is relative.
Right.
These organisms aren't just surviving, right? They're
Right.
thriving in these conditions that we consider hostile.
Right.
So it really challenges our definition of what we even mean by habitable, wouldn't you say?
Absolutely, because I was reading about microbes in permafrost just barely clinging to life in -40 degrees C.
Yeah?
And I thought that was hardcore. But then we see Price and Sauer's research, and they're suggesting that they'd need like 100 million years to cycle through their energy.
Wow.
Talk about playing the long game.
Yeah, it really makes you wonder, what does life even mean in that context?
Right.
But then contrast that, right, with the other end of the temperature spectrum.
Okay.
We've got Mesenopyrus candleri strain 116, and they're just hanging out in those deep sea vents
Oh, wow.
at a toasty 122 degrees C.
What?
Yeah, that's hotter than boiling water.
Yeah.
And it's their happy place, according to Chalkey's 2008 study.
That's insane. It's like their internal thermostats are broken,
Yeah.
but they're not.
No, they're clearly not.
Like something like Planococcus halochiriophilus chilling literally at -15 degrees C. It must have some serious adaptations.
Oh, yeah.
It's not just luck, right?
It's not just luck.
It's like cellular engineering.
Exactly. It's cellular engineering. Mycogic's 2013 research on Planococcus halochiriophilus, you know what they found? It's all about the cellular machinery. Think of it this way. Their internal machinery isn't just tolerant of the cold. It's evolved to work best in those conditions.
Wow.
They've basically redesigned their internal engine for a whole different climate.
Huh.
I mean, imagine if our enzymes could function in sub-zero temperatures.
That would change everything. Okay, shifting gears here.
Okay.
We've talked temperature,
Right.
but some of these extremophiles thrive in pH levels that would make your stomach do backflips.
Right.
There's more than just a little lemon in your water.
Yeah.
We're talking battery acid level.
Yeah, that's a colorful way of putting it.
Yeah.
But you're not wrong. Remember the pH scale, right? Most life exists in a really narrow range,
Right.
but these extremophiles, they're pushing those boundaries to the extreme.
Yeah.
Kwong and his team were studying acid mine drainage systems where the pH was so low, it was dominated by Phorovum,
Okay.
which is a microbe that actually thrives in those conditions.
Thriving in acid, that's wild. But here's what gets me.
What's that?
Even with those, like, extreme external pHs,
Yeah,
they still need a relatively neutral pH inside their cells to survive.
that's right.
It's like they're wearing hazmat suits in a toxic waste zone.
Yeah,
At least that's what Krolwich and some others have suggested.
exactly, exactly. And this internal balancing act is especially fascinating when you think about the early Earth,
Right.
which would have been a much more volatile environment.
Oh, yeah.
So this strict internal pH regulation that we see in these extremophiles, it might be a clue to how early life survived those early conditions.
So from a molten acidic planet to, well, salty French fries.
Oh,
It's a weird connection, but it makes me think about those salt-loving extremophiles. I thought I liked salt,
Huh.
but some of these organisms are living in, like, practically solid salt.
oh, you've seen nothing yet.
Really?
Soda lakes, for instance, can have salinity levels 10 times higher than the ocean.
What?
Yeah, we're talking about a water activity, which essentially measures the availability of water of around 0.4 AW.
Water activity. Okay, help me out here. I barely passed high school chemistry.
Okay, so imagine it like this.
Okay.
Water activity tells you how much water is actually free for life to use. Pure water has a water activity of 1.0 AW. The lower it goes, the less available water there is.
All right.
And to survive, life needs water. The theoretical limit for microbial life is around BANT 0.611.
Okay, so these soda lakes are way below that limit.
Way below.
So how is anything surviving, let alone thriving? Are they just constantly chugging water?
So some organisms, like Selenobacter, have actually evolved to need high salt concentrations to survive.
Well,
This is what we call the salt-in strategy. That is their key to success.
interesting.
No salt, no party for them.
So they're basically the opposite of slugs.
Haha.
But what about those that don't need that much salt?
Right.
How do they handle it without, like, shriveling up.
So they've developed what's called a salt-out strategy. They're essentially excluding salt, and they do this by producing compatible organic solutes.
Yeah.
Oren's research from 2011 goes into this, but think of them as internal balance beams counteracting that high external salt.
Okay.
Halomonas campesilis, for example, can tolerate a huge range of salinity because of these internal solutes.
Huh.
At least that's according to Mormile and his team.
So they've evolved these intricate mechanisms to deal with salt. Amazing.
Yeah.
But we're not done with the extremes, are we?
Not even close.
We're about to dive into something even more intense, literally.
Right.
Yeah.
Let's do it.
Down to the depths where even submarines fear to tread.
Oh, yeah. Imagine the pressure of the entire ocean, right?
Yeah.
Bearing down on you.
Oh, man.
That's everyday life for piezophiles. These incredible organisms, they inhabit the deepest parts of the ocean, right?
Yeah.
Withstanding pressures that would turn, like a submarine, into scrap metal.
Okay, that's officially beyond my comfort zone.
Yeah.
We're not talking about a little squeeze on the subway here.
No.
How much pressure can these extremophiles handle?
Let's put it this way. The pressure at sea level is about 1 atmosphere, right?
Okay.
Or 0.1 megapascals.
Okay.
Thermococcus piezophilus, this is a champion of the deep,
Yeah.
was found thriving at 125 megapascals.
Really?
Yeah. Dalmaso and his team, this is back in 2016, that's over 1,000 times the pressure at sea level.
1,000 times.
Yeah.
It's like being sat on by a blue whale that's wearing a mountain on its back.
It's intense.
But it gets even wilder, right?
Oh, yeah.
I read about life existing at pressures even more extreme than that.
Yeah. So Sharma and Van Lint and their teams found evidence of microbial life not just surviving, but active at a mind-boggling 2,000 megapascals.
What?
Yeah, they were found trapped inside ice crystals, which scientists believe might actually offer them a protective structure against those incredible forces.
But they're basically chilling literally in their own personal pressure-resistant ice palaces. That's just, wow. Okay, so we've covered extreme temperatures,
All right.
pH,
Yep.
salinity, and now pressure.
Right.
Is there anything else these extremophiles can handle? Because it's starting to feel like they're ready for anything.
Don't forget about radiation.
Oh, right.
Yeah, from radioactive waste to the harsh radiation of space.
Yeah.
There are extremophiles equipped to handle even this extreme.
Wow.
Remember, early Earth was bombarded with radiation before the protective ozone layer formed.
Right, like a cosmic microwave zapping everything in sight.
Exactly.
So who are the daredevils that can handle that?
One superstar is Deinococcus radiodurans. This little guy is practically indestructible,
Really?
able to withstand radiation doses that would fry most other organisms.
Wow.
It's all thanks to its incredibly efficient DNA repair mechanisms.
So it's not that the radiation doesn't affect it.
Right.
It's that it can just, like, fix the damage super quickly.
Exactly. Think
Yeah.
of it like a cell with an incredibly efficient repair crew that can instantly patch up any damage caused by radiation.
Huh.
It's a fascinating adaptation. And, scientists like Crisco and Radman, they're studying this for potential applications in, like, bioremediation and even cancer therapy.
That's amazing. They're not just surviving, they're giving us clues about protecting ourselves from radiation, too.
Yeah.
But here's where it gets really interesting. We've been talking about these extremes separately,
Yeah.
but in reality, it's rarely just one thing, right?
You're on the right track. Many extremophiles, what we call polyextremophiles, are adapted to multiple harsh conditions simultaneously.
Really?
Oh, yeah. Take, for instance, an organism thriving in, like, the dry, high-altitude Atacama Desert.
Okay.
It's not just dealing with intense UV radiation.
Right.
It's also facing extreme temperatures, low water availability, and high salinity.
Wow.
That's a polyextremophile for you.
Polyextremophiles. They sound like the ultimate survivors. It's like taking the toughest creature from each environment and, like, combining them into one superorganism.
Yeah, it's no wonder they've captured the imaginations of scientists studying the potential for life beyond Earth.
Okay, let's talk about aliens.
Ah,
Or, to be precise, the implications of extremophile research on the search for extraterrestrial life.
right.
I mean, it's a big jump from a salty desert to another planet.
Yeah,
But I can see how those dots connect.
right. So it's not about finding, little green men hiding in Martian caves or anything like that.
Right.
It's about expanding our understanding of what life could look like
Right.
and where it might exist.
Okay.
Remember those conditions we discussed?
Yeah.
Extreme temperatures, pressure, pH, salinity, radiation. these aren't unique to Earth.
Right.
In fact, many planets and moons in our solar system, and likely countless others beyond, have environments that we would consider extreme.
So you're saying there could be extremophile-like creatures thriving on other worlds? Where should we be looking? We've journeyed to the depths of the ocean,
Yeah,
braved scorching geysers,
it's true.
even ventured to the surface of Mars,
We have.
all in the company of extremophiles.
That's right.
And through it all, we've only just scratched the surface of what these incredible organisms can teach us.
We really have.
It's like we've been so focused on what we consider normal life
Right.
that we've overlooked these masters of adaptation.
Totally.
But how can these extremophiles, these survivors of the most extreme environments, actually benefit us here on Earth?
Well, I think their secrets lie in their incredible adaptations.
Okay.
Take, for example, those enzymes we've been talking about.
Yeah.
These aren't your average enzymes.
Right.
They've evolved to function in extreme temperatures.
Right.
pH levels, salinities.
Yeah.
That would just cripple most life as we know it.
Right.
And that makes them incredibly valuable for various industries.
Okay, so it's like taking a regular toolbox and swapping it for one designed to work in the most extreme conditions imaginable.
Exactly.
What can we do with these specialized tools?
Well, imagine, for example, a laundry detergent that can break down stains in cold water,
Okay.
thanks to enzymes derived from psychrophiles.
Oh, wow.
Or biofuels produced efficiently using enzymes from thermophiles
Right.
that thrive at high temperatures.
Wow.
These aren't just hypothetical scenarios, right? These biotechnologies are already being developed and utilized thanks to those unique properties of extremophile enzymes.
So our laundry gets cleaner, and we move towards more sustainable energy.
That's right.
All thanks to these tiny extremophiles.
Pretty amazing, huh?
It's like they're giving us a helping hand, even though we've only just met them.
Yeah, exactly.
What other tricks do they have up their microscopic sleeves?
Let's talk about bioremediation, the
Okay.
use of living organisms to clean up pollution.
Okay.
Certain extremophiles have this remarkable ability to break down toxic waste, heavy metals, even radioactive materials,
Oh.
essentially detoxifying environments that would be deadly to most life forms.
Hold on. So we're talking about using these extremophiles to clean up our messes.
Exactly.
It's like having a microscopic cleanup crew that thrives in toxic waste dumps. That's a great way to put it.
That's amazing.
Yeah.
It's like extremophiles are not just surviving in these harsh environments.
Right.
They're showing us how to heal the damage that's been done.
Yeah. It's like they hold the secrets, right?
It's almost poetic in a weird scientific way.
I like that.
But you also mentioned something earlier about the origins of life.
Right.
How do extremophiles fit into that puzzle?
So the early Earth was a wild place.
Right.
Much harsher than the planet we know today.
Oh, yeah.
We're talking volcanic eruptions,
Yeah.
meteor impacts, lack of a protective ozone layer.
Yeah.
It was a truly extreme environment.
Right.
And the discovery of extremophiles, particularly those that thrive in those hot, acidic environments reminiscent of early Earth,
Yeah.
has led some scientists to a fascinating hypothesis.
Okay.
You're not suggesting that life on Earth actually started in those extreme conditions, are you?
Some are.
That's a far cry from the warm primordial soup idea.
It is. But it's a possibility that many scientists are taking seriously.
Wow.
These extremophiles, these ancient lineages, adapted to conditions that would have been prevalent on early Earth.
Right.
They might hold the key to understanding the very building blocks of life as we know it.
So instead of a gentle start in a calm pond, life might have ignited in a fiery, chaotic crucible.
It's a much more exciting story, wouldn't you say?
It definitely makes for a more dramatic origin story.
It really does.
But this all ties back to something you said earlier.
Okay.
By studying extremophiles,
Yeah.
we're not just understanding life on Earth, we're expanding our definition of what life is.
I think that's a great way to put it, yeah.
If life can thrive in boiling acid, crushing pressures, and even under intense radiation,
Yeah.
it makes those seemingly uninhabitable planets and moons we talked about seem a little more, well, habitable.
Exactly.
And it's not just about finding life elsewhere.
Right.
By studying the adaptations of extremophiles, we're gaining a deeper understanding of how life responds to stress, how it evolves and adapts to changing environments.
That's right.
That knowledge is invaluable, not just for exploring the cosmos, but for facing challenges here on our own planet.
Absolutely. You know, what's so amazing to me is that they really are more than just survivors.
Right.
They're valuable teachers, guides on this incredible journey of discovery,
Yeah.
a journey that's far from over.
Well, on that note, I think it's time to wrap up our deep dive into the world of extremophiles. It's been an incredible journey. from the depths of the ocean to the vastness of space.
It really has.
And I don't know about you, but I'm feeling a whole new level of respect for these tiny, resilient creatures.
Me too.
It's a testament to the power of curiosity and exploration.
It is.
The more we learn about the universe, the more we realize how much more there is to discover.
Absolutely.
And who knows what other secrets these extremophiles hold, just waiting to be unlocked. So, to our listeners,
Yeah.
keep exploring, keep questioning,
Yeah.
and never underestimate the power of life, no matter how small or strange it may seem.
Well said.
Until next time, keep diving deep.